This is part one of a very special conversation with physicist Abhijit Chavda. Even if you know nothing about astrophysics, but if you want to stimulate your mind, this is the episode for you. Part one is all about the basics. What does the word quantum physics really mean? What are black holes? What are the secrets of the universe all about? A physicist dedicates his own life to understanding the deep secrets of science. When you break down an atom into an electron, a proton, a neutron, what happens if you break down those pieces? What happens if you break down those pieces? How are superpowers even a concept? How are all these science fiction concepts that they show in movies concepts in the first place? That's what today's episode is about. This is part one of our very special conversation with Abhijit Chavda. Hey Ranveer, if you're bringing people on the Ranveer show, they better be scientists. They better be physicists. That's what we got today. Mr. Abhijit Chavda, welcome to the Ranveer show.
Thank you for having me. It's great to be here.
So strange that I discovered you off of videos of history that you've made on your own YouTube channel. Of course, we're going to talk about history in another episode. This one is the introduction of Mr. Abhijit Chavda from a professional standpoint. You're a physicist.
Yes.
What does a physicist do? Because I'm going to ask you a lot of science fiction, black hole, time travel, cosmology questions. But in the modern day, what do physicists do?
So physics is about trying to discover the actual nature of reality.
Okay.
So we have a universe out there and we don't really know how it works. We don't know what it is made of. We have some idea, but there's a lot of missing pieces. So that's essentially what physicists try to uncover. What is the real nature of reality, right? So that's essentially what it is. For example, we see a very big universe out there. We have telescopes and other instruments. We see stars, galaxies, planets, dust clouds, gas clouds, all that. Now, the interesting thing is that whatever we see is less than 5% of the actual universe.
Wow.
So our eyes and our instruments, they allow us to see only 5% of the universe. 95% of the universe is invisible. It's dark, it's missing. And we don't have the faintest clue about what that is.
But when you say it's dark, what do you mean?
Which means that it is not visible to our eyes and our instruments. But we can perceive this missing mass by the gravitational interaction it has with the mass that we can see.
So every object in the world, including this cup I'm holding, including this building, has its own gravity. It pulls
Absolutely.
objects towards it. That's just how physics works.
Yes.
So physicists have realized, okay, there's something massive out there that has its own gravity, which we can feel, which our instruments can measure, but they're not advanced enough to actually see what that mass is.
That's right, yes.
So is when, you say that it's not visible, is it because it's too far away? It's not too far away.
It's not too far away.
It's actually near us.
So there are two kinds of invisible matter.
Okay.
One is called dark matter, which is about 25% of the content of the universe. And one is called dark energy, which is even more mysterious. We don't even know if it's a particle or if it's some kind of property of space-time. So this dark matter that I just spoke about, it's everywhere. I think it's passing through us right now, but it doesn't interact with us because it is a very weakly interacting substance. Maybe it's a form of exotic particles that interacts only gravitationally. So for example, normal atoms of matter, they interact gravitationally, they interact via the electromagnetic force as well. And that's why they're visible. So light is an electromagnetic wave, right? It has the various frequencies, and that's what we interpret as colors. Now these dark matter particles, they don't interact via the electromagnetic interaction at all. That's why even though they are there, we can't see them.
Let me just give an easy analogy for some of the listeners. So would it be like how humans can see 7 colors, Vibgyor, we can see the
Vibgyor.
Rainbow. Possibly there are other animals that can see colors beyond the Vibgyor spectrum.
Absolutely, yes.
Like some animals can see ultraviolet rays, some animals can see infrared.
Yes.
In the same way, you're saying that there is some substance around us which even science is not able to perceive right now.
Yes.
Which is probably beyond human perception, but we're trying to figure out what that is.
We're trying to figure out.
Why it's there.
Why it's there? Yeah, that's a big question. I mean, why is the universe the way it is? So that's a very big mystery, and that's what we have been trying to seek for from time immemorial, right? So that is the big quest in science and physics and all of that.
So modern day physicists, they're mainly concerned about dark matter and dark energy.
Well, physics has a lot of fields. There are fields like condensed matter physics. There's fields like all kinds of fields, right?
Can you explain some with like modern day applications of them?
So, for example, quantum mechanics, quantum physics, which is a very popular subject even in popular discussions and all that. So, the applications of quantum physics are everywhere around us today. This thing works on quantum physics, or laptops, cell phones, washing machines, computers, satellites, nuclear reactors, everything. All this technology was developed using the principles of quantum mechanics. So, these were applied in the form of engineering, essentially. And that's how we have been able to progress. So essentially, the entirety of the progress that we made in the 20th century and after that as well has been built on the top of applications of quantum mechanics. Okay. So we understand quantum mechanics. We can use the principles and the laws of quantum mechanics to build stuff. But the funny thing is that we don't understand how it works. We don't understand why it is the way it is. We don't understand what the equations are telling us. And that's why we have all these different interpretations of quantum mechanics. So it has a practical aspect. It is a very successful theory, but it is one that no one understands.
Okay. But again, what are some of the other domains? Like one's quantum mechanics, one study about dark matter, dark energy. And we'll break down all of these in this podcast. What else is out there that modern day physicists or the top physicists are researching about?
So for example, we have particle physics, nuclear physics. Nuclear physics, we know the applications, nuclear energy, nuclear weapons. Particle physics is about understanding the nature of the fundamental particles of the universe. Like every atom is made up of protons, neutrons, electrons. Protons consist of quarks.
Yeah.
There are 6 kinds of quarks. And then there are particles that mediate the forces and all that. So that is particle physics. We have large machines called accelerators. You must have heard of the Large Hadron Collider in Geneva.
Yeah.
So that's one of the instruments we use to probe deeper into the nature of reality by smashing particles together and seeing what comes out.
Got it.
So recently, the most interesting success that we had was the discovery of the Higgs boson, which was the last missing piece of this standard model of physics.
Got it. So basically, if you keep breaking down an atom, proton, neutron, electron, then you break down those pieces further.
Yes,
and the more we understand those tinier pieces, the better we understand physics. Therefore, the better we understand the universe. Therefore, we'll figure out some applications of that science.
Eventually, there will be applications. Sometimes the applications take a long time to discover. Sometimes it's faster, but eventually there are applications for all of that.
Gotcha. Okay, so this is broadly what physicists divide their work into. Coming back to dark energy and dark matter, you come up as someone who is interested in science fiction to a degree.
I am.
Okay.
It was all that I read when I was a kid. Science fiction. I'm a huge fan of science fiction. Like from the time I was 7 or 8, I started reading science fiction, and it's essentially all I read until I was like 17, 18. After which I went into other things.
Lovely.
So the fiction that I read initially was all science fiction.
Gotcha.
And I think it's wonderful because it's like thought experiments. What if this was true? What if we could do this? And how would things play out?
And they say science fiction books are trailers for the future.
They are.
Things can happen. Like, so we can have intergalactic travel and
Absolutely.
all those things. But again, coming back to dark energy and dark matter, keeping your science fiction fanboy in mind, along with the physicist that you've become, what do you think it is, according to, like, what's your hunch right now, without having done deep research in that field? What do you think are the applications? Why do you think it's out there? Does it have any impact on the human body, mind? What's up?
So as of now, where we are on this little planet, it doesn't impact us at all. But if we were to travel outside our solar system, or if we were to try intergalactic travel, then the thing is that every galaxy is surrounded by a big halo of dark matter.
Okay.
Now, this dark matter, even though it's invisible, it may be like a gas, and gases have temperature, they have density. So if it is hot, very hot, for example, then we may have some problems if we were trying to go out of our galaxy and go to another place. So that is one issue we may face because of dark matter. Now, what is dark matter? People have lots of theories. There are a whole bunch of theories about the nature of dark matter. Weakly interacting massive particles, WIMPs, machos, axions. These are all exotic theories of what dark matter is. I am the co-author of a theory myself. It's called helium. So this hypothesis is that in the very early universe, in the first millisecond or so after the universe was born, in the Big Bang, there were a very large number of, there are believed to be a very large number of primordial microscopic black holes that were created.
Okay.
And it's possible, according to my theory, that if these microscopic black holes formed bound states like atoms, then they may be still around and they may constitute dark matter. So that is one of the theories around today. It's a theory that I have co-authored about 18, 19 years ago.
Wow.
So that is one of the possibilities. So the mainstream general consensus is that dark matter is some form of exotic particle that is not understood.
Gotcha. Okay. And we're still researching, but possibly one of the science fiction applications is that if we create a plane or a rocket that could actually leave the Milky Way galaxy, then at the border of the Milky Way galaxy, that plane or rocket could melt because of the temperature.
Yes, possibly. It could be one issue we could face. So maybe that is not the way to do intergalactic travel. Maybe we need something more exotic, like a wormhole or something. But even that may have some issues. It's all in the realm of science fiction, which meets physics right now.
Lovely.
But we are not in any position to create these technologies right now.
When do you think the human race will be in that position?
We would need a huge amount of energy to create wormholes. So
Hold on. So I just got to give the listeners some briefing about what a wormhole is. So we've actually had a lovely episode with, I think lovely is the word of the day. We had a beautiful episode with Abhi from Abhi and New, and where we explained, the ABCs of a wormhole. So basically say Abhijit sir is at one corner of the universe in a galaxy very far away from the Milky Way. I am on Earth. If I want to go meet him, if I just draw a straight line from me to him, it'll probably take me tens of thousands of millions of light years to go meet him. But what if I take that same straight line, take the two edges of it? On one edge is Mr. Abhijit, on one edge is me, and then I just take those edges and join them through some science. That's basically a wormhole. So we see some, phenomena like this shown in movies like Interstellar, movies like, anything about any science fiction movies, where if you want to go from one part of a galaxy to another, they create basically a door in space. The spaceship goes through that door, and then when it comes on the other side, you're actually tens of thousands of millions of light years away. That's what a wormhole is.
So let me give another analogy.
Sure, sir.
We are on the surface of the Earth. Let's say I want to go from Mumbai to New York.
Got it.
So what I have to do is that I have to take a plane and I have to travel over the curved surface of the planet, and it will take me 15, 18 hours to reach New York.
Yeah.
Now, instead of traveling over the surface of the planet, what if I drill a hole through the planet? So it will allow me to reach faster. So that is one interesting analogy that you could use for a wormhole.
Yeah.
So you are connecting two very different paths of space-time through a doorway or a pathway that you create.
Yeah.
But for that, you need a lot of energy to create that sort of a pathway.
So it's possible in physics, but the energy required is much more than lots of atom bombs even together.
So there are certain solutions of the Einstein equations of general relativity which allow you to create wormholes. These are called wormhole solutions. But there are problems in that because the thing is that this pathway is very unstable. And you need something inside to keep it open, otherwise it closes. It closes as a black hole. So it may also be possible.
As a black hole, as in it becomes a black hole.
It becomes a black hole. It pinches off. See, it's a doorway. It's a tunnel. But then the tunnel pinches off and it becomes two black holes on two opposite ends.
Got it.
So that's what happens. So you need something to keep it open. And there's also the possibility that if you try to travel through it, it becomes unstable. So the act of trying to travel through it itself may make it unstable. So there are these theoretical problems, these issues. So we are not entirely sure if wormhole travel may be possible, but there are some other solutions and some other possibilities that may make it possible.
Like, sir?
Like, for example, there is a hypothetical thing called a cosmic string. It's not part of string theory, it's something else. So it is hypothesized that in the very beginning of the universe, after the Big Bang, there were these structures called cosmic strings that were created. At the time, the universe was very small. It was like the size of a marble. And enormous amounts of cosmic strings were created with tiny wormholes. Now, as the universe expanded, these cosmic strings, they stretched and the wormholes went far apart in the universe. Today, they may be millions of light years apart. But because of the cosmic strings, these wormholes may be open. So if you can locate one of these wormholes and cosmic strings, then these will be open. These will remain open.
I want to highlight something you said at the start of the podcast, which is that 95% of the universe is undiscovered.
Yes.
So, and all we can see is the solar system. man has only gone as far as what? Like the moon? Like
The moon,
himself?
yeah.
And probably ships we sent out, I think, have crossed Pluto, right?
The furthest is the Voyager spaceship, which has essentially reached outer space now, interstellar space. So it has gone past the boundary of the solar system.
Wow.
So that's the furthest we've gone. But it's really just one footstep in the grand scheme of things.
Yeah, and you're saying that out there in that massive black ocean that we call space, there are possibly these doorways that if you enter one, we don't know what will happen. And two, it'll probably get you to some other part of the universe.
Absolutely, yeah.
Or another universe itself.
Well, that is an entirely different possibility. We don't know if we can actually travel to a different universe because we don't even know how big our own universe is. The visible universe is a certain size. The universe is 13.8 or 9 billion years old, and the visible universe has a radius of about 90 billion light years. But the actual universe may be much larger than that. It may even be infinite. We have no clue. So about other universes, we would be able to explore them only if we can explore our own universe. But that itself is not possible because the universe is expanding. And the expansion of the universe is making certain parts of it inaccessible. Because the further you go away from Earth, the further the space-time is expanding. And at some point in time, it's expanding faster than the speed of light.
Wow.
So because of that, it may not be possible to even do that.
Do you think that you're what, like how old are you, sir?
I'm 44.
44. So do you think by the time you're 84, like 40 years from now, we would have made significant strides in all these kind of things that we're speaking of, or at least some of them?
I hope that we colonize Mars by that time. I mean, not colonize, but we travel to Mars and we establish a foothold over there. But interstellar travel, I don't think it's going to be possible anytime soon. At least in the next 100 years. We are just taking baby steps right now. See, what we have is chemical rockets. Chemical rockets are very, very rudimentary machines. We need a lot of chemistry, a lot of chemicals, and they are very unstable. They can explode at any time. So it's a very difficult and delicate operation just to put a human being into orbit or to send somebody to Earth or Mars at most. But to have the technology to go beyond the solar system or beyond the galaxy is going to require a whole different kind of physics and a whole different kind of technology that we don't have right now.
Got it. And it's primarily about powering the existing machinery that we have. So we probably have the machinery, but we don't have the power.
We need immense amounts of power to go beyond the distances that we are talking about.
Got it.
And chemical rockets are not going to fit that bill because first of all, they're too slow and they require a lot of fuel. So ideally what you want is something like the annihilation of dark matter, or I would say the annihilation of antimatter with matter. So that is a very pure form of energy.
What is antimatter, sir? Okay, first explain what matter is, then explain what antimatter.
So the matter that is around us is the ordinary matter, but we know that there are antiprotons, anti-positrons, anti-electrons, and neutrons. So if you create an atom with antiprotons and positrons, it's an anti-atom.
Okay.
So for example, hydrogen, it has one proton in the nucleus and it has an electron that goes around the proton. That's the simplest atom that we have. Now, instead of the proton, if we take an antiproton and we put a positron around that, that's an anti-hydrogen atom. Okay. Now, the property of antimatter is that if it comes in contact with ordinary matter, it instantaneously annihilates and it releases a huge amount of energy.
Antimatter releases energy. So say that the negative hydrogen, the antimatter hydrogen meets the positive hydrogen. There's an explosion, you're saying?
Yes, they become just pure energy.
Both of them?
Both of them. They spontaneously annihilate each other.
And this is like, okay, so basically, before the atom bomb was created, Einstein figured out how to create an atom bomb, how to create nuclear energy. And then the application of that was the atom bomb. Now, because of advancements in particle physics, people have figured that, oh wow, now this can happen. This is also another way of creating energy. And this is a huge amount of energy. Therefore, maybe there are applications like interstellar travel.
If we can figure out how to store antimatter, for example, because the moment antimatter is exposed to the atmosphere, it will explode. It will annihilate.
Got it.
So we have to keep it in a perfect vacuum. If even one molecule of oxygen or air comes in contact with it, it's going to create an explosion.
How big is the explosion?
It depends on the energy that is inside the molecule. For example, a proton has a certain amount of energy, 511 MeV, mega electron volts. Electron has a certain amount of energy. So it depends on how much antimatter comes in contact with ordinary matter. And we can calculate the amount of the explosion.
But is it bigger than an atom bomb?
Yeah, it could easily be bigger than an atom bomb. It can be a very, very powerful source of energy if we can use it right. So we need a certain kind of engineering which has not been invented yet to store it and then make it react with matter in a certain way.
Beautiful. This is where the machine guys, which are the engineers, come in touch with the scientists, which
Absolutely.
are the research and the learner guys, and create something for the sake of science.
All progress depends on engineers. The ideas come from theoretical physicists, but to make these ideas practical and apply them in the real world, you need engineers. So engineers are very important because of that.
You know, when people go like, "Oh, why are engineers in other industries?" It's for the same reason.
Yeah.
That in engineering college, you're taught three things. You're taught jugaad to get out of trouble, which is just do shit to get out of trouble. You're taught mental toughness to be able to, you know, deal with stuff in life, and you're taught this solutions.
Solutions, yes.
Like find the right way to do it. Find the architecture to do it.
Absolutely.
Any thought you have, it could be a thought about relationships or space, can be broken down into structure, I feel, which is something that engineering college
Mental
coding,
models and structures and all that. Yes, absolutely.
like visualizing architecture around thoughts. That's
Absolutely,
what,
yes. That's a mental model, isn't it?
Yeah, 100% so. So coming back to this conversation, you know, you spoke about intergalactic travel, how they've sent out that spaceship which has probably crossed where Pluto is, Pluto's orbit, and it's gone slightly beyond the solar system. When scientists plan a mission like that, first of all, do you know when it was sent out?
It was sent out sometime in the 1970s.
Okay, so when they sent it out back then, with what purpose is it sent out? Is it just sent out with this open purpose of go see what's out there?
The purpose for these Voyager spacecraft was to take photographs of the outer planets.
Okay.
Jupiter, Saturn, Uranus, Neptune, these four. And if anything else comes out in the way, we could do that. These missions got us the first images, detailed images, color images of Jupiter, Saturn, Uranus, and Neptune.
Okay, and
That was the main purpose of this mission.
Got it. When you hear about these planets like Neptune and all these gassy planets,
Gas giants.
gas giants, gassy planets, gas giants planets. You know how there's like theories about them that if you go inside the gases at such a high temperature that you'll die in like a second or you'll melt away in a second. How has science figured all that without actually sending something in?
So what we do in astrophysics is that we apply the laws of physics and chemistry to models of a planet. Okay. So we have first figured out how the solar system actually formed. What we know is that there was typically when a solar system forms is that you have a giant cloud of gas, which comes from somewhere. It essentially comes from the death of another star. Okay, then this gas cloud coalesces together under the force of its own gravity. We have observed this astronomically. Okay, and then slowly all the heavier elements, okay, like carbon, silicon, phosphorus, all these things, they combine together and they form planets. But at the core of this thing is a giant ball of hydrogen, which under its own gravity undergoes fusion. And that is the formation of a new star. Okay, and then you apply the laws of physics to all these planets. What kind of, is it a rocky planet? Then it will have a certain kind of geology. Is it a planet with a lot of gas? Then it will have different characteristics. And you can model them using the laws of physics, plasma physics, condensed matter physics, and all that, to essentially to judge what kind of properties they will have. And then you can see the spectrum of the light that comes from Jupiter and Saturn. So you can determine using that what kind of gaseous composition it has. You know the size of it, so you know how much pressure will be inside. And using all these different pieces of information and data, you can figure out very precisely what kind of properties this planet will have, and at what depth, what temperature you will find. And if there is carbon in Jupiter, at the very core of Jupiter, it will be squashed together so hard, it will become diamond. So it's very likely that Jupiter has a diamond core.
Yeah, the diamond rain that we hear about on all these planets, it's the same logic, I'm guessing.
Yeah.
That when carbon is found in the atmosphere, probably the atmosphere turns it into diamond because of the pressure.
Yes, when it goes to the depth where there is that amount of pressure, then it will become diamond.
Lovely. I've got to ask you about the next general domain that you spoke about, quantum mechanics. What does this even mean to an average person who's just getting into physics? How would you explain quantum physics, quantum mechanics, these things?
So quantum physics is the physics of the ultra microscopic world.
Even smaller than an atom.
Not smaller than an atom, the molecular level, atomic level, and subatomic level. Okay. So it is a very, very counterintuitive and very perplexing theory. but we know it works. So, for example, if I have a particle in a box, let's say I have a molecule of oxygen in a box. Now, typically, when you put a tennis ball inside a box, you know exactly where it is, right? If you can see it, if it's a transparent box, you know where it is. And even if the box is closed, it's going to be in one position in the box, one location in the box. However, because of the laws of quantum mechanics, if you have an oxygen molecule in a box, it could be in all kinds of different positions at the same time. It is not localized. Okay, so there is something called the wave function, which is denoted by the letter psi. So the wave function is essentially a field of probabilities, and every part of the box, the particle will have a non-zero probability of being there. So the particle is in a superposition. It's in a superposition of all kinds of different states at the same time.
Got it.
So that is one of the strange things about quantum physics.
So in the real world, things can only be in one place at one time. Like this
Yes.
cup, it doesn't follow the laws of quantum physics. Therefore, it's only on this table. But the moment you start following the world of quantum physics, once you go down to that level, suppose Abhijit sir and me become as small as an atom, then the laws of physics change. Where the same cup, if we throw it into a box that's governed by quantum physics, there might be 5 cups that we'll be able to see together.
You will not be able to see 5 cups at the same time. When you make an observation, you will see only 1 cup. Okay. So the entire superposition of probabilities will collapse and it will become just one. But as long as you don't observe it, it's in a multitude of states at the same time.
Got it.
So that's how it is. So that's just one of the strange things about quantum physics. There are a whole, for example, you can have barrier transmission. So if you have a thick barrier, and you shoot a particle at it, there is a possibility, a non-zero finite probability that the particle will just go through the wall.
Got it.
That is something we don't observe ever in the real world, right? But the thing is that the real world, the world that we observe every day, it emerges out of the laws of quantum mechanics. That is the fascinating thing about it.
So first of all, so this is very Xmen-esque. By that, I mean that, there's these characters in Xmen which can pass through walls.
Yes.
There are characters in Xmen which can be at multiple places together. There's a character called Nightcrawler. So suppose I'm Nightcrawler, I can just like kind of explode into a gaseous state, and then suddenly I'm in that room instead of this room. So somewhere, I mean, the only reason I'm highlighting X-Men is to make the average listener understand what quantum physics laws can possibly be like. And I'm sure there's 1,000 more like this. Like the example you gave about looking at that box with a cup inside it. The cup, actually, if you look away, it's all over the box. But the moment you put your eye on it,
It resolves into one place.
Yeah, it'll all converge into like one cup. It'll say, no, I'm just like right here. Similarly, I'm sure that the particle passing through the wall is just the second example out of like 1,000.
There are 1,000. There are many really weird examples. The more generalized form of quantum mechanics is called quantum field theory. And according to this theory, this entire world is an illusion. Particles themselves are fiction. The world is made up of fields. So there are fields everywhere, and the interaction between these fields causes the laws of physics as we know it. And the particles themselves are nothing but waves, localized waves in the fields. So that is the more general version of quantum physics. It says that there is no such thing as empty space. Vacuum itself is fiction. Everything is fields. There are fields that permeate everything. And that is the most successful theory that we know of in physics.
Successful, as in it's proven again and again.
Yes, we can predict the properties of nature extremely precisely using quantum field theory.
Got it. And a lot of spiritual people also highlight the quantum field theory as a proof for spiritual thought. Like when you say omnipresence, that there's something all around us, that there's cosmic energy all around us. In the world of spirituality, it's called cosmic energy or omnipresence. In the world of science, it's called the quantum field, which basically means that you and me, while we're talking, we're probably made out of the same energy. We're made from the same energy. And only when I'm putting my eye on you, can I see all that energy converge into one man, and reverse. When you're looking at me, you can see all that energy converge into one person.
We are manifestations of the same fields, right? And in Indian philosophy, there is this concept of consciousness. So we don't really know in science what consciousness is. We don't even have a definition. But in Indian philosophy, it says that consciousness is something that permeates the universe. So there is a consciousness field in the universe. And wherever we have individual people, there is a concentration, localized concentration of consciousness. So that is in a form a field theory. But it is a field theory that is a part of philosophy, not science.
Got it. We actually had this podcast way back. I think this was our fourth or fifth podcast ever. You're the 105th or something.
I see.
So it's been a long time since then. But that podcast was about this, the quantum field theory.
Okay.
So there is this whole concept that I believe that there is some machinery all over the world which is capable of measuring something within the quantum field theory. Is there something like that?
I am not aware of exactly what that is.
So the episode was with one Mr. Abhijit Pradhan, who studies these things a lot. But again, he studies it from a spiritual perspective.
Oh, okay.
So basically, just before 9/11 had happened, that machinery had caught a change in the quantum field all over the world.
I see.
Where, so they say that, okay, if truly you and me are made out of that same energy, we are connected in some way.
I
So
see.
someone even in Africa or in Japan was feeling something different right before 9/11 happened. Like a big worldwide catastrophe that you would eventually notice. When we talk about things like intuition, sixth sense, I'm dead sure that the quantum field theory has some role to play in all that. Or, just feeling a connect with another human being. That's what separates humans from animals, that we're more collaborative, we look out more for each other, we're more empathetic, we're able to express art which can be created by one human and appreciated by another. So somewhere, when you really break down your human experience, there is some deeper level of connection you have as compared to most animals, if not all.
Yeah, absolutely. The human consciousness is very different from the consciousness of animals. The thing is that these theories are valid theories, but they don't come in the field of science.
Okay.
Right. These are theories of spirituality and philosophy.
But do you think it doesn't come into the field of science yet?
Yet, absolutely. I am not against it. I am not a disbeliever or non-believer. It's just something that's beyond science. So let me tell you the difference between science and philosophy.
Sure.
Science deals with the observable world. It deals with observable physical objects, okay, and the laws that govern them. Philosophy also deals with observable objects, but also with non-physical objects like the soul, like consciousness, like
ego.
God, like ego, and all of that. And a physical theory has to be falsifiable. So if I were to claim that there is a Hawkins pressure cooker circling the sun between the orbits of Neptune and Pluto, that theory is a valid theory, but it cannot be falsified, right? So that is not a physical theory. That's not a scientific theory. You can call it a philosophical theory.
Got it.
Okay, so that's the difference between science and philosophy. Once you understand this boundary, then things become more clear. So when you talk about consciousness and empathy and intuition and all that, these are philosophical concepts. These are not scientific concepts. But it doesn't mean that someday science will not be able to explain them. Right now, our science has limitations because of the limitations of our intelligence and of our instruments and our understanding. But someday in the future, we may be able to understand other things as well.
Yeah. So how Elon Musk is coming out with Neuralink. Neuralink
Yes.
is a device that fixes issues in someone's brain. So someone is dealing with some brain-related issue, like say brain-induced blindness. If you get head damage and then you become blind, or
Yes.
you get you have a road accident and then something goes wrong in your body. You become, say, paralyzed, or you can't hear, or epilepsy or something like that. So Neuralink can fix all these issues.
It may be able to fix these issues, possibly.
Okay. So I think Elon did a podcast with Joe Rogan where Joe Rogan asked him, so can you basically fix any issue with the brain? Elon said, yeah, as far as we've progressed right now, we can.
Wow.
So that's a cool kind of progress that's happened in the world of science, which has its applications in the world of human beings or the human experience. But my point is, if he's so confident about it fixing some brain issues, I am sure they're also thinking about the version 2.0 of that same technology, which will be enhancing the brain. Like once you fix the brain, what's the next step? You make it a supercharged brain, superhuman brain.
Yes, but what are the applications, I wonder, and who benefits from this? So, for example, first of all, I am very skeptical about hacking the brain, because the brain has evolved over millions of years to function in a certain way. If you inject raw data into the brain or you try to modify things, it's going to interfere with the functionality of the brain. For example, we talk about there is this popular notion that we use only about 5% of the mental capacity, and if we could hack it and make it 100%, we could become superhuman and we could be almost godly. The thing is that that may not be true. There is a reason why the brain is the way it is. There's a reason why we need sleep. For example, right now there is this research being done in neural networks, artificial intelligence, right? Something came out very recently that even a neural network needs a period of rest when it is not actively computing anything. If you make a neural network compute constantly beyond a certain time limit, it starts producing garbage data. But if you give it a period of rest, sleep, so to say, for a few hours, then it goes back to computing the way it was supposed to. So sleep seems to have a very, very profound impact on consciousness, on the way the mind works and all that. And neural networks mimic the human brain. So if you try to overclock the brain and try to make it process things beyond what it's designed to, it may actually end up causing insanity or something like that. So we have to be very careful about these things. Yeah, sure, we have the application, we have the chip that we can implant in the brain, but what are going to be its implications when you actually put it inside a person and experiment? I mean, we are human beings, not guinea pigs, right? So I would say we need to be cautious about trying these technologies.
Yeah. You gave me a whole other podcast idea to do with you. And I'm very fascinated by the world of biohacking. I think you, me, and I have this friend of mine who's a biohacking entrepreneur. Three of us should do a podcast together.
Let's do it, sure.
Yeah, and then we'll see where it goes. It'll be an iconic piece. But coming back to astrophysics and your life as a physicist, so this is kind of an intro for the audiences on all those subjects. Of course, we're going to talk about aliens and time travel and all those things, sir. But right before we enter that domain, so you've explained quantum physics. You've explained the theories of particle physics to a degree. We've spoken about, I think, wormholes?
Wormholes, black holes, yes.
Black holes. Is there any other domain of study that physicists are involved in that we haven't mentioned?
Oh, there are all kinds of domains. Chemical physics, biophysics also is one of the...
Biophysics.
Biophysics. For example, if you have the human ear, we perceive sound because of the vibrations of the eardrum. And the vibrations are transmitted via nerves to the brain. We perceive light because of photons that enter the cornea, the retina, and then they are transmitted as neural signals to the brain. Let me tell you something very strange. We perceive the world in a certain way, but it may not be the real nature of the world.
Like you and me might be seeing different colors.
Perhaps, but the deeper thing is this. What is color? Color is nothing but a certain vibration of the electromagnetic field. And that is interpreted by our brain as colors. Okay, now let's say, we know the colors of the rainbow, right? VIBGYOR, Vibgyor. Is there white in there? Is there black, gray, brown in there? Is there pink in there? These colors don't even exist on the rainbow, and yet we perceive them. These are non-spectral colors. These are invented by our brain to make sense of certain connections between spectral colors. So our perception is essentially color coding in the real sense. So for example, let's say you have a cell phone and you have a user interface which you use to send emails and all that. But inside the cell phone, you have a very complicated chip. Right? It's a chip with lots of circuits in there. It has layers of software. It has ones and zeros. It has voltages and all that. Now, if you had to toggle voltages and circuits to send an email, you would never be able to send it. So the user interface gives you a very simplified version of what's inside, right? Similarly, maybe our senses give us a very simplified version of what the real world is like. Maybe it's too complicated for us to process cognitively in real time. So these are all the things that people are researching into.
Which is why dark matter and dark energy, is something that our minds and bodies haven't perceived yet.
Absolutely.
But if our minds get evolved to a certain degree, maybe we'll look around us and there might be new colors.
But we would need a large amount of processing power. So our brains would have to evolve, first of all, for us to be able to see all that.
So there are spiritualism theories that state that, okay, now you and me are in this room, so we're in a physical realm, but around us there also exists an astral realm, which is where the theory of ghosts or interdimensional beings come in, which says that in this room there might be a ghost present with us, but we're not able to perceive it. Or there might be an interdimensional being, like say Hanumanji might be here, but we may not be able to perceive it. There might be some other being that we don't even know. Aliens might be watching us right now because they might be interdimensional beings, but we may not be able to perceive it. And this theory kind of echoes, again, another concept from spiritualism. I think that as the world progresses, we are seeing this whole wave of spirituality kind of take over the world. But there are a lot of men of science, women of science, people of science who are embracing spirituality from a scientific perspective. So I feel like it's going to converge and then theories are going to come out like that.
So one of the things you will see if you study the history of quantum physics is that quantum physicists, the pioneers of quantum physics, were invariably drawn towards Indian philosophy and Indian spirituality. The reason for that is that quantum physics, once you reach a certain amount of maturity in your study of quantum physics. So, for example, I have been studying quantum physics for the past 25 years.
Wow.
Okay. Once you reach a certain amount of maturity, you will realize that I can use quantum physics, I can use it to solve problems and all that. But the moment you realize what it's trying to tell you, that's when you realize you don't really understand it at all. And the implications are so strange that you feel suddenly lost. Okay, for example, there's something called the wave function. I spoke about that just some time ago. The universe also has a wave function. Now, like I said, a particle in a box is at all places at the same time. But when somebody observes it, it becomes resolved as one particle in one location. So you need an observer to make a particle emerge in one place or be in one place. Otherwise, it's everywhere. It's not real at all until somebody observes it. Now the universe has a wave function. The universe too has a wave function. And we know the universe is real. So does it mean somebody outside the universe is observing it to make it real? So when you reach this level of thought, everything you believed in suddenly disappears and you're lost, And then you seek answers in spirituality or in some kind of philosophical tradition.
Which the human mind might actually understand because we understand stories and like fictions.
So in the entire world, there are lots of philosophical traditions, religious traditions, but the only system of philosophical schools of thought which has explored ideas like this is the Indian school of thought. That's why all these scientists like Oppenheimer, Heisenburg, etc., they eventually all gravitated towards Indian philosophy. For example, Werner Heisenberg, who is one of the pioneers of quantum physics, I believe he came to India on a lecture tour sometime in the 1930s. And he paused in Shantiniketan. He met Rabindranath Tagore. And he poured his heart out to Tagore that I have invented this theory, I'm part of the building blocks of this theory, but I don't understand it at all. It's so strange. It cannot be true. So he explained what strange things are there in the theory. And Tagore said that our philosophy talks about these things. So that's how you gravitate towards a philosophical tradition that has possibly some explanation. Now the thing is this, Indian philosophy is about exploring the inner universe. Close your eyes, meditate, and explore the inner universe. And the theory is that the inner universe and the outer universe are connected. So by exploring the inner universe, you may actually gain ideas and perceptions about the external universe and insights, profound insights. So that is a theory. And it seems to have very interesting ideas that really gel with what quantum physics tells us. And that's why quantum physicists eventually, at some ways, they all gravitate towards that.
Gotta ask you the next obvious question, which is that those theories that you spoke about, that Heisenberg met Rabindranath Tagore, they spoke about things and then Tagore said, okay, we have already learned these things in our spiritualism or whatever. Could you highlight some of them? Like, or your guesses about some of them after studying so much quantum physics?
Like, for example, being in two places at the same time and having extra dimensions, for example, and all kinds of other phenomena that come out of quantum physics. For example, the observer effect, that the particle doesn't even exist until you observe it. The universe doesn't exist until an external observer observes it. And the age of the universe, the Big Bang theory says that the universe is 13.8 billion years old, but it may go on for billions of years more. But in Indian cosmology, we have a Brahmand which is created from Brahma. Vishnu creates a Brahmand, and every universe has one Brahma associated with it. And the life cycle of the Brahmand has a certain finite span. And Indian philosophy talks about a multitude of Brahmands, which is the multiverse. Multiverse comes out of quantum theory. So if you look at all these ideas, there are lots of parallels, incredible parallels between Indian philosophy and quantum physics.
Another podcast idea. This is like a whole other, and this we're going to do with Manish Pandey, who's an expert on the Indian school of philosophy.
Very interesting.
I need to do 3% podcast with you, sir, because I don't have it in me to keep up with your level. I'm just the host, but I will bring other experts and let's do these 2% podcasts
Absolutely.
at some point. So as for this episode, because it's just an introduction,
I want to kind of move away from these scientific topics and say two things on a personal level. Can I call you like a big brother?
Absolutely, please.
I bow down to you and I bow down to your knowledge. As your younger brother, I hope that this glamour of the YouTube world takes whatever you've learned and your communication skills out to the world. And for that, I actually request the listeners to spread word about this particular episode. On a personal level, these kind of episodes don't get views. These kind of episodes aren't spoken about till they're discovered eventually. And we've had a bunch of these episodes. We've had one with Gad Saad. Have you heard of him?
Of course, I have,
Yeah,
yes.
the evolutionary psychologist. He's like one of
Yeah.
the top guys in evolutionary psychology.
I follow him on Twitter, yes.
Yeah, same. And you know, these episodes aren't appreciated by the audiences, but I think they will be. Over 5 years,
Eventually, yes.
people will look back and say, yo, how did I miss out on that? Why am I only watching these Bollywood actor episodes? So my point is, you requested scientists. We've brought on like great communicators, scientists, all that. Spread the word about it to your friends, to your family. And now we'll move on to science fiction.
Ladies and gentlemen, that was the end of part 1 of a special conversation with Abhijit Chavda. Part 2 is coming out very soon. It's going to include all your questions, which we took out from Twitter. It's also going to be centered around aliens, time travel, and those kind of topics. You guys are going to enjoy that one even more than this one. So watch out for part 2 of this conversation.